Alright everyone, welcome to the last GPU talk of the semester. Today I'm going to go over the PyCUDA module, which is based in Python. It's like a Python module like any other module except, well, GPU accelerated. So I'm going to, basically today is just going through a bunch of code. I break it down into sections, but basically I'm going to demonstrate a bunch of code, and I'm going to tell you about sort of why PyCUDA is, the advantages of PyCUDA. It encapsulates a lot of the memory transfer to from the GPU and the parallelism and all kinds of stuff. And there's this dynamical systems modeling package that some people built on top of that. And I'm going to allude to that a little bit at the very end. All right, so let's get started. So PyCUDA is a Python module, like I said, and currently our Impact 1 server has it. Impact 2 does not have it right now, which is unfortunate because Impact 2 is more up to date. But we'll see. I'm going to try to get the IT guys to get on that to hopefully, when they have time, install it on Impact 2 as well. So there are a bunch of things you can import here. You can, to begin, you could just say from PyCUDA import star, or you could import the driver, the auto-init submodule, and the compiler submodule separately. They do different things. And just to show you how you might use this, we're going to begin with a 4x4 array of random numbers. You want to convert these into 32-bit, well, floats. If you want to generalize your code, some cards are really old and they only support floats. They'll usually automatically demote from doubles to floats, but just to make sure you're safe, this is usually a good thing to do. So, allocating device memory is easy on PyCUDA. You just say you have a memalloc function, and you give it the number of bytes, and you assign that to some new object. And that object lives on the GPU. And what you're working with in Python is a pointer to that. Now let's see. So CUDA is really PyCUDA driver. So this is really PyCUDA driver memalloc, by the way. Yes. So CUDA is my submodule of driver, which is a submodule of, let's see. Yeah, driver is CUDA, and it's a submodule of PyCUDA. And sending information to the device is also easy. There's this CUDA memcopy host to device. That's what HTOD stands for. Copies the thing on the right to the thing on the left, just like CUDA memcopy does as well, but the syntax, as you can see, is much easier to remember, and this is much more shiny because we're in Python now. Now, for some kernels, in the general case, you will have to write them. This is one of those cases where, it might be, well, there are ways to do this with built-in functions, but in the general case, you will actually need to write your own kernels to run something in parallel using PyCUDA. But you can just store that kernel as a string. You just take one function, and you give it a linear array. This can exist in your mind. Float A can exist in your mind with basically any number of dimensions that you want, but it's going to be read in to the device as a linear array, and you have to worry about the indexing. But that's okay, because that's how you would want to copy things to the GPU anyway, until NVIDIA gets better at handling multidimensional arrays. Now, all I'm doing is I'm saying let IDX be the index along A that we're at right now. You can map that back to the 2D array representation if you like, and we're going to just take all the elements and multiply each by 2 and do all those multiplications in parallel and return the result. Very simple. And remember, the triple quotes are a good way to make sure that you can use a multi-line string to define your kernel, because writing that all in one line using a single quoted string is not very readable. Anyway, So my kernel is called doublify for obvious reasons. And I'm going to turn this into a callable Python function. There's this function called getFunction. I already forget what mod stands for, so I'm going to show you. So we imported, where is mod? Yeah, mod must not have gotten on the slide, but I think it's in the compiler. And other examples we'll probably see, but I think that this is a, that if you said, I think if you said compiler.getFunction, you would be okay. But I would definitely make sure that, or source module. So we imported source module. Sorry, I'm flipping back and forth for the guys who are looking at this from the web, but I'm pretty sure that source module is the real thing that I'm aliasing with mod here. So if you said source module.getFunction, I'm pretty sure that that would take this function doublify and turn it into a callable Python function. Anyway, so you take a string as a kernel, and it compiles that function in a Python object, which is pretty cool because now you can call the kernel from within Python. In this example, I'm going to use one grid, one block, and 4 threads in each of the x and y directions. By the way, using threads in different directions, pretty difficult to keep track of in C, at least from my perspective. You have to create these dim objects for each of blocks and threads if you want to do several dimensions in each one. In Python, it's much easier to specify threads in the x direction and the y direction, which help you conceptually when you're working on code. So that's what I'm doing here. So there's this block, and it's a tuple with 3 numbers, and that's the number of threads in each dimension. You could presumably define more blocks also, but I'm not showing that here. So notice I'm calling this function like I would a normal Python function, this func. I'm passing in the data and the level of parallelism that I want, which is the block argument here. And for the results, to grab the results from the GPU, I need sort of an empty container, or I put container in quotes because I'm not using that in a technical sense. I need an object to get the memory back into. So I'm just going to create an empty array with the same size as A. And I'm going to use this CUDA memcopy function. I'm going to copy the GPU version back. Memcopy device to host. And I'm going to print that out. I'm going to print out both. As you can see, this array in the top is the doubled one, and the array in the bottom was the original one. All of that happened in parallel. Very easy parallelism if you like Python, which is the power of this module. I really wish that R had the same levels of parallelism. I mean, there are things like GPUs, GPU tools, but it currently does not have any GPU acceleration for its core native routines. For statisticians, we would want something like that. If you could take the apply functions like apply and sapply and tapply and all those kinds of things and accelerate them, then that would probably be a really useful thing to have. Anyway, so we sort of encapsulated a lot of this parallelism in the previous example. Yes? I'm not sure. I imagine that they're pretty much the same. I'm not sure about it though, but I mean, you could do your own performance studies. I'll show you a bit how some code to do that later, but you're still compiling C code and you're still running C code, and there's transferring memory, to and from Python, to and from your Python workspace on the CPU, but CPU GPU transfer is slow anyway. So I think I mean, I haven't studied this rigorously, but my guess is they're about the same, and they're both very good. So you can add another level of encapsulation with these driver in, out, and in-out functions. They're a little bit of a syntactic sugar for the memory transfer functions, CUDA memcopy functions we looked at earlier. Here's an example. So in this kernel, I am, this is what I meant by mod. Okay, so mod is a source module function, which in the source module function takes whatever string represents a kernel here, turns it into an object, a module, source module, and then this source module object has a get function method that you can use to turn kernels into Python objects. And that's it. That's the sort of what mod is more clearly laid out here in this slide. What I'm doing is I'm just taking a kernel, and it takes arrays of floats A and B, multiplies them element-wise to get this destination, and each pairwise multiplication happens, all the pairwise multiplications happen in parallel, element-wise rather. So, and I get this callable object, this callable function, multiply them out of all of that, and A and B are just going to be my random, arrays of random numbers that I'm going to multiply together, and my destination is going to be this empty container to write back to. Now, ordinarily you'd have to do, at this point you would have to allocate memory, transfer memory, call the function, then write the memory back, free all the memory. If you use driver out and driver in, you don't need to worry about all of that. You have the objects, you can just call the function. You can say multiply them, and if you cast each of these, well, not cast, but if you turn each of these objects that you want that currently exist on the CPU as Python objects, if you just call driver out and driver in on them, then you can just call the kernel without doing anything fancy, which is nice. Use driver in for the arguments, and driver in for the arguments that you want to write to the GPU, driver out for arguments that you want to write back to the CPU side, and driver in out if you want to do both. And the block and grid arguments say that I'm calling blocks in 3 dimensions. I'm calling them with 400 threads in the X direction, one in the Y direction, one in the Z direction. And again, the grid object tells me that I have one block in the X direction and one block in the Y direction. So if you want to have multiple blocks, you would use this grid argument at the very end. And so when I print out the destination minus A times B on the CPU side, I get all zeros because they're the same. Just a proof of accuracy, a little bit. But see how easy that was? That's much easier than programming in CUDA C directly. I mean, so this takes the flexibility of CUDA C because you have these, you can do whatever you want in this string that specifies the kernel that you write. But you don't have to worry about 95% of the code, which was just the setup and cleanup, which is taken care of with driver in and driver out. Very powerful. So here's another example. We begin with a 4x4 array. And what I'm just going to do is I'm going to multiply everything by 2. This is doublify again. Only this time, I'm using the driver in-out. At line 21, I'm using CUDA.inout of A, and the in-out driver, like I said before, is used to write things to the GPU and then write them back to the CPU in the same place. So I've just condensed the previous code that I showcased before. And as you can see, original array on top, doubled array on the bottom, that looks right. Okay. You thought that was shortened and condensed. There are even more ways to do this. So let's see what that looks like. So there's this GPU array feature of the GPU array submodule of the PyCUDA module. And it works like this. There are some stereotyped kernels that you might be using a lot, and you don't need to write those out in C fashion over and over again, because these are very common, and PyCUDA already has them. Some of them, well, that's for kernels. For this, actually, I'm getting ahead of myself. Oh, maybe I'm not. So what this does is, line 6 creates an object called a GPU array out of a 4x4 array of floats. And once you have this object, your kernels, you get some kernel methods for free. So you can write whatever you want to happen in parallel on the device in Python fashion. So you can just say 2 times a GPU, and the .get method just grabs the result. So super easy to do element-wise parallel multiplication on the GPU. And then your result gets stored in this a.doubled here, because that's the way it's written in line 7. But yeah, that doublify function just got shortened to 9 lines, including all the imports. So this GPU array object is great because it has all these built-in methods that allow you to call very common kernels that you could, not only built-in ones, but ones that you could write on the fly like this, just 2 times a GPU. And the output's analogous. The output's correct. I mean, one array's, double the other. So here's what I call short examples. The first few examples were short. These next ones are going to be a little longer, but still short. So since CUDA C is really CUDA C++, you have C++ features with all of this. You can create, let's see, I begin with this kernel that has an increment function that works on all numeric types, and maybe some character types if you want to, but I'm just going to take, no matter if x is if t is the float type, or t is the int type, or t is the double type, I'm going to take some x of type t and just add 1 to it. I can define device functions in addition to kernels here. It'll create a source module out of all of this. This is kind of like a shared object or a dynamic library for the R programmers out there who write R packages and accelerate them in C by writing dynamic objects or shared libraries. Dynamic libraries, shared objects, same thing. Anyway, so, but if you use the C++ features in CUDA C++, you need to wrap your kernels in this extern C thing. That's so PyCUDA can actually find the kernel function. The same thing applies if you write GPU accelerated R packages. You need, if you use C++ features, then you would need to wrap this thing inside an extern C. Anyway, so all this kernel does is it just increments an array element-wise. So it takes this array A, goes through in parallel, and for each thread gets a unique place in the data and increments the value there. And this last argument tells you sort of what you can do with extern C with that feature. So you can choose to include it or not. Much of this is review, obviously. I'm going back to the sort of long implementation of all of this. I'm just working with regular Python arrays here. And just a note, remember this .copy function. I think I talked about it last time. So be careful of shallow and deep copies, and be sure to keep track of what's on the CPU and what's on the GPU, because Python tries to micromanage that for you, and you want to be exactly sure of where your array is, whether it's on the CPU or on the GPU, what things are deep copies, what things are shallow copies. And this is an example I pulled online of how to do that right, being really sure to use the .copy function. Anyway, as you can see, this was the original x, this is x incremented. Pretty simple. That looks right. 1 is added to everything. Here's a matrix multiplication program. Now, I didn't go over matrix multiplication in parallel in code before. Several months ago, actually, at the very beginning, I remember I went over some common algorithms, or just really simple algorithms that you could accelerate using GPU parallelism. That was sort of a codeless intro to GPU parallelism. It was one of the first talks. And I talked about matrix multiplication, and this program accelerates matrix multiplication in almost that exact fashion. So here's the kernel. So this is going to multiply A and B together to get C, where all these things are matrices. And notice this time, it's really easy to use, since we're in PyCUDA, it's really easy to use threads in multiple dimensions. So you can say, well, you can take care of this on the Python side really easily. So I can go ahead and use these thread indices in each dimension. So tx and ty are the thread indices in each dimension. P-value is an unfortunate name, but I didn't write this code. P-value is just something to store the current element of the matrix, of the return matrix. Now, this is actually there are fewer layers of parallelism in this matrix multiplication implementation than the one I described. This is just parallelizing across rows and columns of B and C, of A and B. Normally, what I would do is I would take a row of A and a column of B and assign that to a block, and within that block I would parallelize the dot product that gives you the matrix, right? You might not have to. I think I have later slides telling you how to do this in parallel, just with a built-in function. I'm almost positive it's available. I was reviewing the slides. I think I saw something like this, and I will, if it's not there, I'll find it. But I'm almost positive it's there. Anyway, so what this does is each thread gets one row from one matrix and one column from another matrix, and then it loops through naively, and it sums all the products of the elements in the rows and columns, stores that in p-value, and p-value is now the relevant entry of the matrix. Notice here that I have this parentheses matrix size. That is another mechanism for passing values to the GPU, for example, simple parameters like matrix size, and I'll show you how to do that. So whatever matrix size is, the value gets inserted here. So This matrix size in this case is just going to be 2 for this example. And I'm going to create a bunch of arrays. I went over this before. And I'm going to create this C on the CPU just to compare to what the product that I get on the GPU. Now, here is where I worry about matrix size. There are a bunch of values that you can do there are a bunch of things you can do, a bunch of values that you can put in a dictionary, and that dictionary gets passed into the kernel, and you can reference elements like matrix size with parentheses, sorry, not with parentheses, with percentage signs, like I showed before. So matrix size lives in what looks like a dictionary, and I'm using this function kernel code template %, to create that, and that dictionary lives in this object kernel code. And when I compile, when I create this source module out of this, I'm going to pass in kernel code. Let's see. Oh, kernel code template was our original, I'm sorry. This kernel code template was our original string defining our kernel. And then I also have this dictionary element called matrix size. I combine those two to make this object kernel code. I can pass that into the source module function, and I get the source module out. So think of matrix size as a macro that I can pass into the kernel. That's sort of what I would think of as passing macros in. And I can create a matrix mul by the as a callable Python function, getMod as usual, and I can call it in the usual fashion. And now the block argument, this is something that we hadn't done in the previous examples. You got to make sure to give matrix size threads in the x direction and matrix size elements in the y direction. If whatever you were counting on here to have multiple threads in the x and y direction, you have to make sure you do the correct thing in this block argument when you actually call that Python function. Now I just print everything out, and here are the matrices. And the difference is 0 again, so the code that I pulled from online worked. I didn't actually write any of this code myself, but I ran it. Anyway, so PyCUDA conveniently also has a curand, or a curandom submodule, which is based on curand and the CUDA C++ framework. So it's called curandom, that's your submodule. And it has this function rand. I'm going to call that function curand for the rest of this code. And I can do things like assign arrays of random numbers on the GPU. So A, B GPU, and B GPU are arrays of random numbers that I can just create by calling this curand function, which is pretty cool. You don't have to worry about setting up random number generators or anything like that. It just uses curand automatically. This example also has a different way of defining kernels. You can sort of do a shorthand for a kernel where I is going to be maybe your thread index. You can think of it as your thread index, and given all of that, you can call this function element-wise kernel. The first argument is a string that has all the arguments to your kernel. The second string has what it actually does, and the third is going to be the name. After you do that, you can continue setting up all your arrays to make this work. And what I'm going to do is I can, if I want to, I can just run through this example and I can call that function. Here's a different example. Reductions are easy, and you can write them in shorthand in the spirit of this element-wise kernel function. Reductions happen very easily in a similar way. So let's say we have two arrays, and this isn't actually a reduction on, well, it is. You can do, a dot product is a reduction. So let's take a dot product of A and B. And this reduction kernel is not only a reduction, it's a map and a reduction. So the map expression is going to be this map x argument, and the map is just going to multiply these things pairwise, and then the reduce is going to be the sum. So you could reduce this to just a reduction, or just a map if you want, but you have a really neat map reduce function in reduction kernel. You create, so kernel here, KRNL, is now a function reduction kernel, and you can use the .get method if you want to call that and get values out of it. So people in big data and all that are making a big deal about things that mostly just do map reduce. I mean, or it's the most important, where map reduce is the most important feature. I mean, you get things like a Hadoop and Google's map reduce. They worry a lot about mapping and reducing. This is something that does that, and it does it in parallel. Anyway, you have scans also. Scans, remember, prefix sums. You do partial reductions along the length of a vector. You can use this inclusive scan kernel to create, for example, a scan on a sum, and you can use that and run it in the same way. And compare it with the cumulative sum down here at line 14 from Python. Yeah? No, I actually don't mean different GPUs. So actually, I may have misspoke or misled you when I made such a connection between Hadoop and Google MapReduce and this. So what this is doing is distributing data to threads and blocks, not even to different cards. So we only have one node here. But you could do this, I mean, you could write this to distribute data across cards, across graphics cards, and then reduce across the cards as well. Mm-hmm. Exactly. And this won't work on as large of a data as Hadoop can do. But if you choose, you might be able to make this a piece of what happens in a single node. Exactly. Exactly. I've directly experienced that issue. I was working on a parallel MCMC this summer, and I couldn't store all the results of my chain because I ran out of memory. And yeah, and that wasn't even that big. That was a few 100,000, maybe even a few million points. But I mean, that's not very big. But I ran out of memory anyway. So, yeah, I mean, I don't know if Hadoop or MapReduce have GPU accelerated, capabilities, but if they didn't, I mean, a good place to maybe do that would be within each of the nodes. So, okay. Oh, great. So, so if I wrote a binary and I could use that would work just with Linux pipes and stuff, then I could make this work. Mm-hmm. Right. Mm-hmm. Mm-hmm. Oh, so it apparently will work if you have the hardware, if you can make a binary that works Linux style. That's really good to know. Cool. Now, you mentioned before that maybe, is PyCUDA as fast as regular, CUDA C? Well, you can find out. There are ways to measure speed in a way similar to what you've already seen. And that's what this example does. So I'm going to use a GPU array for this. I'm going to keep track of sizes and times and all those things. The sizes are kind of like the size of the computational load. And yeah, let's get to the main example. So power is the order of magnitude of your computational load. So the bigger the size, the more one operation is going to take. And I'm going to work with GPU arrays of size, and I am going to generate random numbers, arrays of random numbers of that size. And I'm going to time that. And for the, and I'm going to repeat this count times, where a large count would be really intractable for a large size, so I pick count based on how big the individual commands are going to be. But notice here for lines 28 through 39, so I'm working with events. So an event start, I call my event start, and another event end, and start has a record method, and there's an end has a record method too, and I synchronize those two end at the very end of this. That's much like you have seen, very much like what you've seen in the past a few lectures ago when I went over timing this stuff in CUDA C. It's almost the exact same thing. So drive was the driver module. So you just use the driver module to get events. And you can function event and record are exactly the same thing. And the only thing is you don't have to worry about cleanup. You don't have to worry about freeing things because we're in Python. That's happy. And that's the main point I wanted to get across for here. You can go through this code if you like. But yeah, they're very easy ways to time your GPU code in Python. So, and you can also use Python to query what devices are available to you, like this. It's in the driver module. You can use the count method to get the number of devices. You can get the names and compute capabilities, total memory, all of that good stuff is available in the driver module. Maybe easier than trying to go into the software development kit and hit device query. You can extract whatever information you want. And this is a very easy way to do it. I don't know if I went over compute capability, but it's very important. It's kind of like a version of CUDA. It's sort of what it is capable of doing. And, well, the higher the better. All right, that was my main PyCUDA stuff. There's this software package called ABC-SysBio. Some of you may be interested. This is very specific, but for people who are watching this video, maybe that would be of interest. So ABC-SysBio is a GPU-accelerated package that does approximate Bayesian computation and it estimates parameters in biological dynamical systems. So in this figure, you're considering, kinetics of biological reactions, maybe enzyme kinetics or something, and you want to estimate these rate constants up here in the upper left. And you might look at models that predict concentrations over time, and this package does that. It has a rejection sampler and sequential Monte Carlo for parameter inference and for model selection as well. So it's ready to use on Impact 1. I don't think we have it on Impact 2. But it's ready on Impact 1. So there are a bunch of commands available. You can use it for multiple interfaces. If you're within Python, you can import an ABC-SysBio module. You can also use it through the command line with these two commands. So to learn about it, you really have to dig into it yourself. There are a couple of resources here that would be very nice to check it out. This website and this paper would be really getting it from the horse's mouth. I'm not going to go over it in too much more depth. This is very specialized. And for input files, because you need XML files as input for this module, you can look online, and I've got many. I've got several input files. Anyway, here's what we went over. Just a rundown of PyCUDA, hopefully justifying why I went over Python so much last week, or 2 weeks ago. So if you want to follow up on this, I got most of my examples from this website, from A. Klockner. He's responsible for the documentation as well. There's a lot of documentation and examples on PyCUDA. You can read more about ABC-SysBio in this paper. And all of my examples are online on this page. And that's it for the semester. Thanks all for coming, and I hope you learned useful things. Yes?